Okay, let's continue to talk about branch instructions, right? Last time, we were in the middle of talking about branch instructions, right? These 6. So using these 6 branch instructions, you can do what? You can compare, unsigned numbers and signed numbers. And there are 6 different conditions. Probably you want to check in high-level code, right? So in total, these 12 conditions can be checked with these 6 instructions, right? Sometimes you want to use just this sudo instruction, the sudo, and compiler will convert that sudo instruction into actual RISC-V instruction, right? Like this, right? So by looking at these names, it is very intuitive. If you want to check equality, then using BEQ. Inequality, not equal, right? And then greater than or equal. So, same name, right? Greater than or equal. And U. If you have a U suffix, you are comparing A and B are unsigned, numbers, right? And if you want to check greater than condition for, unsigned numbers, then you can use BGT greater than and U, right? So these two are unsigned numbers, right? Then assembler, right? The assembler will translate that into actual RISC-V instruction. So there are 2 things from a programming point of view. It is not that hard because it is very intuitive instructions, right? You can select right instruction depending on your needs, but we are not satisfied with that programming, assembly programming only. Because we are interested in hardware design. So think about that. To execute these instructions, to execute those instructions inside the CPU, what kind of operation, what kind of functionality should be implemented inside the CPU, right? So BEQ, this one. Taking this one as an example. So you want to check equality, right? These two are equal. Then you want to branch to this label, skip. So, skip the instructions between BEQ and add and execute addition instruction. If condition is satisfied, right? S0 is equal to S1, right? So taking this one as an example. So what kind of functionality, what kind of operations you have to do for executing this instruction? 2 things, right? The first one, okay, let me remove this one. The first one, you have to compute. You have to calculate branch destination. So in this particular example, the skip, right? What is the location of the label skip, right? And then branch destination is computed. Okay, let me finish this. Branch destination, because branch instruction, right? Branch instruction is trying to update program counter with that location, the memory location, depending on condition, right? If the condition is met, if S0 is equal to S1, then you want to set program counter to that skip this label, right? So branch destination, what is the location? What is the location of this label skip, right? So CPU should compute branch destination. And second, condition check. So in that example, CPU should compare S0 and S1 register. These two are equal, then you are supposed to update program counter. right? So condition check and branch destination computation. So two things should be done by hardware inside the CPU for executing, branch instruction. Right? So far so good, right? So let's first talk about okay, this one, branch destination computation. Okay, let me write it down. Let me write here. Branch destination computation. Program counter should be set to skip, and second, condition check. Right? So two things should be done by hardware. So first, branch destination. If you check out the next slide, so branch destination, according to RISC-V architect, okay, so let me go back to here. So if you check out the branch instruction, first these two operands are encoded in RS1 and RS2, and this label skip is encoded in the immediate. So before we talk about the instruction, the detail of branch destination, a branch instruction is using B-type encoding format. B-type is variant of that S-type encoding. If you remember, S-type encoding is used to provide what memory write instructions, store word instruction, store half word instruction, store byte instruction. So compare these two. So let me open up. So check out this, right? So compare S-type and B-type instruction. Very similar, right? Very similar, but the small difference in the immediate, right? So in the B-type, so immediate 12 is 1 bit, and then 6 bit, right? So only 1 bit is different. Immediate 11 is encoded here, right? To place immediate 12, right? So immediate 4 to 0, immediate 4 to 1, then there's no immediate 0, 11, right? So anyway, it is very similar, but a little bit nasty in terms of immediate, right? Because it is distributed, somewhat nasty in a way, right? So anyway, a branch instruction is using B-type encoding, and then this label is encoded in the immediate. So what do you mean by a label? So let me write down BQ, S0, S1, then skip. There are some instructions, and this one is destination skip, right? Where you have addition instruction. Add T0. So the information you are encoding in the immediate, so in the instruction, so it is a little bit nasty, right? In the immediate, right? Immediate, and then here immediate, right? So the information you are encoding, so you want to encode what? 12 to 1 is 12 bit. Here, I think 7 bit. Here, 5 bit, right? So anyway, when you design hardware, CPU, you have to take out this 7 bit and 5 bit, and you have to rearrange to make it neat and nice like this. So you have to rearrange, right? So rearrangement is very easy, right? It's just wiring in the right way. And then, important thing. So immediate, what kind of information is encoded in the immediate? So RISC-V architect decided to encode the distance from current location current location to destination. That offset. That offset is encoded in the immediate. Okay. And then so one important thing, why 12 to 11? So go if you say offset, right? How far from current location to the destination, but not number of byte is encoded in the offset. The information is encoded here is number of 2 byte. Number of 2 bytes. Number of 2 byte information is encoded here. Immediate 12 to 0. Why? Number of 2 byte? Because remove this. If you remember, where is that? Risk 5. Okay, here. Right? If you remember this slide, risk 5 is providing this base instruction. This base instruction is mandatory, and then depending on your needs, you can add instruction extension, like M extension. M extension is providing multiplication and division instructions. And then F extension is providing floating point operation instructions. And the important thing is this one, C extension, compressed instruction. This one, 2 byte instructions, 2 byte. Okay. Integer instruction, each instruction is 4 byte in size, right? Each instruction 4 byte. Compressed instruction, 2 byte in size, right? So what RISC architect decided to encode in the immediate is number of, in other words, number of compressed instructions. Compressed instructions. How many 2 byte instructions could be there from current location, from this location to the destination? How many 2 byte, how many compressed instructions are there? Again, integer instruction. BQ is integer instruction, right? That is translated to 2 byte instructions, 2 compressed instructions. Right? This one addition instruction also, 4 byte instruction, which is equivalently two compressed instructions. Right? So in this way, you can count how many effectively how many 2 byte instruction could be there from current location to the destination. That is encoded here. Right? Okay. So check out, how destination is computed. Should be computed inside the CPU. Destination. Look at this. This one, green box, is a CPU. Okay, green box is CPU. Then you have a branch instruction inside the CPU. So rearrange that, take out, this 12-bit and rearrange to make it neat and nice like this. Then based on this MSB is the immediate 12, right? MSB, most significant bit. Hardware should do sign extension. So you want to create 32-bit, and then add the location of the branch instruction. So this location plus this offset, that is the operation you want to do. That is one branch destination. Right? So this star is program counter, right? current location of a branch instruction, then offset, right? So 32-bit, the program counter is 32-bit. So somehow you have to, from this 12-bit information, somehow you have to create 32-bit, right? So you have to do sign extension. And then one thing you have to be careful, because the information is encoded is a number of 2 bytes. So you have to add, you have to append 0 at the end, right? You have to append 0 at the end. Then that is how many bytes away? How many bytes away from current location, right? Offset in bytes, right? Not 2 bytes, just byte, right? So for the purpose, you have to append 0, right? So appending 0 is very simple operation, right? You just very simple in hardware, right? So you have 12-bit, then 0, right? 0 just add, right? And then sign extension, right? So these two should be added together, right? You need adder, and then output will update program counter, branch destination, right? Branch destination, right? Branch destination will update program counter depending on condition, right? So in this case, in this example, it is just updating program counter, but you have to check condition as well. Okay, this is the logic. This is the logic you have to design inside the CPU, right? Again, a current location of a branch instruction plus distance. The reason why you do sign extension is because sometimes the destination is in the forward direction, positive direction. Sometimes destination could be, in the backward direction, skip, right? Backward branch, right? So minus, right? So computer is using 2's complement number system, right? And then that information is encoded in, immediate, right? So that is why you are doing sign extension. So first thing is done. First thing, right? Then let's talk about second operation, right? Condition check. This one is a little bit complicated. But I assume you have taken, digital logic design and understand, overflow and underflow. So I don't want to spend, I don't want to spend 1 whole hour discussing that, underflow, overflow for sign number and sign number. But underflow, overflow, that mechanism is essentially used to check the condition, right? So let me explain simple thing. Then you can figure out, complicated thing. Simple thing is unsigned number comparison. Complex one is a sign number comparison. But there is a solution. I already told you, right? Number 36. So this is a table you have to refer to and implement that condition. This one, the one in green and in orange, that should be implemented in hardware to check the condition. But let me explain. Simple one. Higher and lower. This one would be simpler. Higher or lower. Okay. So before that, let me briefly talk about computer arithmetic. Zero, assuming 3-bit computer. 3-bit computer, right? 3-bit, right? Data is represented in 3-bit. That means unsigned number case, unsigned integer, right? So numbers you can represent 0 to, +7. So 1. So 7 is 1, 1, 1 in binary. 0 is 0, right? So what is the overflow and underflow, right? So think about this example. What example? You are adding what would be good? 2 plus 2 plus 3. About that. So what is 2 plus 3? Starting from graphically, right? Starting from location 2, you are moving 3 steps forward, right? 1, 2, 3. So this is a solution, right? 5. But what if you add, this number, 2 plus 6? So the actual solution is 8. But 3-bit computer cannot represent this number, right? Because 7 is the largest number it can represent. So anyway, let me do the same thing. Starting from 2, you are supposed to move 6 steps forward, right? 1, 2, 3, 4, 5. Then there's nowhere to go, right? Then the computer is doing what? It wraps around, right? Then so 1, 2, 3, 4, 5, 6. So computer shows this answer. But in this case, we say overflow, right? Overflow happens because the actual answer is larger than the maximum value the 3-bit computer can represent. So that is overflow condition. How to detect overflow? Very simple, right? If the carry is equal to 1, so think about this, right? So you are doing addition. 2. What is 2 in binary? 0, 1, 0, 6, 1, 1, 0. So you are adding these two. 0, 0, 1 carry out. So 1, 1, 0. The final carry out. So we are talking about this carry, right? Carry is 1. Okay. And then what if you are doing subtraction? So addition works like this, right? Subtraction case. I'm trying to explain on the flow condition. If the actual answer is the less than the smallest number 3-bit computer can represent, then we call that on the flow. Okay. Done. So let me explain with an example. What if you do this? 2 minus 1. What is 2? What is 2 minus 1? Starting from 2, you are moving 1 step backward, right? So that is the answer, right? 1, right? So we don't have any problem, right? Computer. So 3-bit computer can represent this number 1, okay, right? But what if you do this? 2 minus 3. Then actual answer is minus 1. But computer cannot represent this minus 1. So that is, we say on the flow happened, right? So 2 minus 3, right? Let's do the same thing graphically. Starting from location 2, you are moving 3 steps backward, right? 1, 2, then what? There's nowhere to go. Then computer wraps around, right? So 1, 2, 3. So computer will show you this information, 7. And underflow happened, right? So how to detect underflow? How to detect, right? So overflow is detected if you do addition, right? You do addition, 2 plus 6. So actual answer is 8, right? But it is showing 0, right? You do addition, then the value is larger the answer is larger, the maximum value 3-bit computer can represent, then overflow, right? And then that is detected by, by this, carry is set to 1 after addition. Then we say, overflow happened. How about on the flow? Right? On the flow, uh, with this example, 2 minus 3, right? So you are moving, starting from 2, you are moving 3 steps backward. But in computer, you have to think about, computer arithmetic, not human arithmetic. The computer, human, you are moving 3 steps backward. But computer, right? Computer is using what? Subtraction is done with the addition, with the 2's complement number system, right? So 2 plus 3 is actually what? 2 plus what? 3 is what? Minus 3, sorry. Minus 3 is what? Okay, so starting from plus 3, 0, 1, 1, flip all the bits, right? 1, 0, 0, and add 1, right? So that is, minus 3. So 5 actually. So computer is doing addition or subtraction, right? So 2 plus 5, right? Starting from 2, 1, 2, 3, 4, 5, right? Same answer, right? So I told you, starting from 2, 3 steps backward. 1, 2, 3, that answer, right? So because computer is doing this operation, addition, right? Starting from 2, 1, 2, 3, 4, 5, right? So how about the carry bit in this case? Carry bit is set to 0 on the flow, right? If carry bit is set to 0 after subtraction, again, if carry bit is set to 0 after subtraction, be careful. We are talking about computer arithmetic, not human arithmetic, right? So computer is doing this operation for this, right? So carry out, no carry out, right? No carry out. Carry out is 0, right? Because answer is within that range, right? So after subtraction, the carry out is set to 0, then that is on the flow condition, right? On the flow, right? So let's talk about now this one, unsigned on the flow, right? Unsigned the lower, that condition, right? Unsigned the lower. So think about this, lower, right? BLTU, okay? Less than, unsigned number comparison, right? So you want to compare these two. And then condition is met, then pro and counter will be set to this skip. Assume taking these two as an example. X2 contains 2, and this one 3. Then less than condition, right? Less than. Confusing. Okay, sorry. Less than, right? This one is not, condition is not met, right? So LTU, BLTU, less than, condition is not met, right? Condition is not met, LTU. Condition is met, okay? Unsigned lower, unsigned lower, okay? Unsigned lower, unsigned lower. Carry bit is clear, sometimes confusing. Unsigned lower, right? 3, 2. Okay, unsigned lower. Condition is met. Then carry 3 minus 2. 3 minus 2, then carry is supposed to be 0. Carry is supposed to be 0, then condition is met. LTU unsigned lower. Unsigned lower. Confusing, right? 3. Who is what? 2 is hold on. Okay, let's continue. You know, I'm not sure why always confused with the simple arithmetic. Anyway, BLT, right? BLTU. So taking these two numbers as an example, 2 is less than 3, right? Less than 3. 3 is bigger than 2. So, you know, for this operation, right? To execute that instruction, you have to do what? Uh, you know, you have to make CPU to do subtraction. You read that instruction, and then you know, you read ALU, make ALU to do subtraction. So you know this operation 2 minus 3, right? And then computer will do using 2's complement number system. Computer will do what? Addition operation for this subtraction. So if the carry bit is set to 0, that means this condition is met. This condition, right? 2 is less than 3, right? Condition is met, right? So according to this table, right? If carry bit is clear, carry bit is 0, then condition is met, right? How about this condition? Higher. How about this condition? Higher condition. Higher condition. Risk 5 is providing what? B, G, BGE or BGT confused. Okay, let's go back to PG. What is the instruction? Okay, PGE, right? That is a real instruction. PGEU, PGE. Let's talk about that. .36. Okay. B greater, higher or same, PGEU. So you want to check this condition, X3, and skip, for example, right? So greater than this one, greater than or equal, right? You want to check this condition, right? But now, you know, forget about this equality. Equality is very simple. After doing subtraction, if carry bit, okay, I think that is included. Okay, so let me do this. Zero bit, zero flag is set to what? Zero flag is set to 1, then equality, right? But you don't have to even look at zero flag for this, I think, because you know carry flag. If carry flag is set to 1, that is including the equality condition, right? So you know, let me explain your example. Take a look at this. First, you know, greater than, right? 3 minus 2. 3 and 2. This one greater than. This condition is satisfied, right? This condition is actually satisfied. 3 is bigger than, greater than 2, right? So you have to make CPU to do subtraction. 3 minus 2. Then computer will do addition for subtraction, right? So 3 plus minus 2. Minus 2 is what? If you do the math, minus 2 is what? 0, 1, 0 plus 2. So 1, 0, 1, 1, 0, 6, right? 3 plus 6. That is actual the computer arithmetic, right? So starting from 3, you are moving 6 steps. 1, 2, 3, 4, 5, 6, right? 6. The answer is 1. So answer is 1. And then you got overflow, right? Because computer is doing this arithmetic, right? So carry flag is set to, in this case, carry flag is set to 1. Okay, how about when, what if these two are equal, right? For example, you are comparing these two, 3 and 3. So by checking only carry flag, that condition is also the checked. I think yes, because think about computer arithmetic, 3 minus 3, right? Then 3 plus minus 3. So what is minus 3? Okay, minus 3 here. Minus 3 is 5, right? So computer will do 3 plus 5. So starting from 3, you are moving 5 steps forward, right? 1, 2, 3, 4, and 5. So you got 0, but overflow happens, right? So when these two operands are equal, carry flag is set to 1. So by only checking carry flag, you can tell this condition is satisfied or not. Okay, so this is the one. So in this way, you can check. You can check the condition. You can check the condition for unsigned numbers. Right? But the signed number comparison things are a little complicated. So I like you to think about that. So for signed number comparison, we are using what? Overflow flag, V flag, right? What is V flag? Check out. Check out computer logic design course. Teaching this one, digital logic design. ID 코세 221 and same password ESCA. Okay. So if you scroll it down, then the lecture slide adder and subtractor. Check out adder and subtractor. Okay, CLD subtractor. I think if you check the subtractor. So we are using the same thing, overflow, underflow mechanism. So overflow and underflow, right? So on sign number, things are simple. And sign number, a little bit complicated. But overflow happens. Taking 3 computer as an example, right? 3 computer, 3B computer. So 8 different values can be represented. Right? 0, 1, 2, 3. And then -1, -2, -3, -4. So 3B computer, right? For sign number, right? So this one is 0, 1, 1. Actually, this one. Okay, and -1 is what? 1, 1, 1. So let me write down, right? So 0, 7, 6. 7 is what? 1, 1, 1. Right? And 0 is 0, 0, 0. 3, 0, 1, 1. One side number, right? 4 is what? 1, 0, 0. And then you do the math, right? So if you compare these two, So sign number on sign number, it looks like this, right? So that is map 2, that is equivalent to this, right? 0, 1, 2, 3, same 0, 1, 2, 3, right? Same number, right? 3 zeros, 0, 0, 1, 0, 1, 0. And then this one, right? From 4 to 7, that is, map 2, this one. 4 is this, and 7 is -1. Sign number, sorry, sign number. So if you add the two numbers, if you add two positive numbers, for example, 2 plus 3, for example, starting from 2 and 3 steps forward, but one step, there's nowhere to go, right? Then wraps around 2 and 3. So computer will show you this answer, but that is overflow condition. We got overflow. Okay. How about on the flow? On the flow, if the answer is less than the smallest number, 3-bit computer can represent that is on the flow, right? So example, right? Minus what? Minus 1 plus -3. Starting from -1, you are moving 3 steps backward, right? So 1, 2, sorry, 4. 1 minus 4, right? 4 steps backward. 1, 2, 3, nowhere to go. Then 4, right? So you got this answer. But that is on the flow. So on the flow, you are adding two positive, right? So sign bit is 0. But actual answer, 2 plus 3, so right? You got what? 1, 2, 3, right? So this number, -3. So sign bit got changed, right? So we are using that, that characteristic. Two negative numbers. Sign bits are 1, but actual answer 1, 2, 3, 4. Actual answer sign bit is 0, right? So sign bit got changed, right? So that is underflow condition. So underflow overflow can be detected using this sign bit, source operand sign bit and output. But better probably formula is using carry, two carries, last carry out and second last carry out. You are doing XOR, then there is overflow flag, V flag. So using that overflow flag, you can check going back to this. There is a V flag, right? V flag. So using that V flag, you can check these all different conditions, right? And RISC-V is providing two instructions, right? BLT and BGE, right? X2, X3, then skip, for example. X2, X3, skip. So BLT, BGE. So what? BLT, less than. So, negative flag is not equal to V flag, then this condition is met, satisfied. Less than, and this one, BGE, greater than or equal, right? So these two are equal, negative flag and V flag, right? Again, these flags, right? These flags are coming from ALU. ALU is taking two source operand, right? RS1, RS2, and then actual output, right? So let's say A and B and Y, 32-bit each. Then in addition to, this actual output, ALU is generating negative flag, zero flag, carry flag, overflow flag. So for signed numbers, right? So according to that table, you can use negative and overflow flag, right? For condition check. Okay, that is the one. Let's go back to. So that is the one, right? So we have, I think we have finished our branch instruction discussion, right? Two things, right? Branch destination computation, and then condition check. Condition check can be done by using, those flags depending on instructions, right? And then condition is met, then you are updating, the program counter. So taking, let me show you one example. So it is probably boring. So let me show you this. So I'm not sure how effective it is because the encoding is very nasty, right? Bit type encoding. The immediate, right? The distance. Distance is encoded in the immediate, but in the machine code, immediate is distributed in a nasty way. So I'm not sure how effective it is to show you machine code, but let me try. So what we are doing is BEQ X2 X3 L1. Then we have one instruction between destination and branch instruction. L1. And here we have add I instruction like this. Then I told you, right? So what kind of information is encoded in the immediate, right? So the distance from current location to destination, this offset. Okay. Probably you can do the math first, right? So let me compile it. Save and Control B. So we can do the math first, right? So starting from, so what kind of information is encoded in the offset? Number of 2 bytes. How many 2 bytes are there? In other words, how many compressed instructions? Compressed instructions are there from current location to the destination effectively, right? Not actual compressed, but effectively, right? So starting from here, each RISC-V instruction is 4 byte in size, right? So starting from here, 4 byte and 4 byte. So destination is 8 byte away. 8 byte away from current location. 8 byte away, right? So 8 byte away from current location, PC. And what kind of information again is encoded? 8 byte, right? So 8 byte, how many 2 byte? How many compressed instructions are there? So divide by 2. So 4, that is equivalent to 4 compressed instructions. 4 compressed instructions, or 4 2 byte instructions. Right? 4 instructions are there. So let me explain this, right? So this is the one I want to explain. Okay. So hardware, right? So PC. Let's say the location of branch instruction is, let me cook up this 100 for simplicity. Our program counter 100. And then 8, right? Forward direction, positive, right? So 8 should be added, right? Then So this one is offset, sign extended offset, and then this one is 108. And let's compute immediate from this information, right? What is 8 in binary? 1, 3 zeros, and everything is 0, right? And according to this, right? So 0 is appended by hardware. So the information you have to encode is this 12-bit. This one is encoded in the immediate 12 to 1. Okay, 12 to 1. So, this information. Let's go back to our actual encoding. So, 12 to 1, right? So almost everything is 0. Everything is 0 except this information. Okay. This one, immediate 12 to 1. 1, 2, 3, 4, 5, and 11, right? 12, sorry, 12. So 4, 2, 3, 1, that information. Okay, that information should be encoded 4 to 1 right here. 4 to 1. So 7-bit OP code. And then adding this 11, so 8-bit, right? 2 hexadecimal number. And then we are expecting 4 in next hexadecimal number, right? So let me show you. Check out dump. Okay, so look at this. OP code 7-bit and immediate 11. So these two immediate 11 and OP code. That is 8-bit. That is 6, 3. And next number 4 to 0, 4-bit. And that information should be encoded 4, right? So that is why we have 4 here. Everything, uh, and then upper what? How many? Upper 8-bit, 4-bit, and 8-bit, right? 12-bit. Sorry. So 4-bit, 12-bit, right? 4-bit, 12-bit. 4-bit, sorry, 4-bit, 8-bit, 4-bit, 8-bit. So 12-bit. So 8-bit supposed to be 0. So this information. So all 0. Right? So try to figure out the machine code, right? So machine code is uh, machine code is generated based on this premise, based on this encoding format. You can check it out. You can do the math yourself, right? Okay, that is about branch instructions, conditional branch instructions, right? Then before we talk about unconditional branch instructions, jump instructions, let me talk about set less than instruction. So these 4 instructions actually not branch instructions, right? These 4 are data processing instructions, data processing. And the reason why I put these 4 in branch instruction slide is because what? Because let me first explain. So number comparison, less than. Right? Set less than, right? So operation is check out this example. So you want to compare these two, less than condition, right? If S0 is less than S1, you want to set T0 to 1. Otherwise, you want to set T0 to 0. So depending on condition, destination register is set to either 1 or 0. Very simple operation, right? Set less than. If you have a U suffix, U, then the numbers you are comparing are unsigned numbers. Okay, So we have two instructions, U and U. And you have I suffix. That means, second operand is included in the instruction itself, is I type encoding. Right? So first source RS1, and then second source immediate, right? And these two are signed integers, RS1 immediate, and last one, IU. Okay, immediate, second operand is immediate, and then these two are unsigned numbers, right? So operation itself, very simple, right? So the reason why I put these instructions in branch slide is because, set less than condition, right? Using the same mechanism, overflow, underflow, same mechanism, you can implement, you can design, CPU, right, for executing these four instructions. So for example, to execute SLT instruction, you make CPU to do subtraction. Okay. SLT T0, S0, S1. You want to check this condition, right? Check this condition, then set T0 register to either 0 or 1. Condition is met, then set this one to 1. Condition is not met, set this one to 0. Simple, right? Then for executing this instruction, what you have to do inside the CPU, right? You make CPU to do subtraction, S0 minus S1. Same thing, right? And ALU, then ALU will do what? S0, S1, ALU do subtraction. We are not interested in this output, right? So you have to check out these flags. So in this case, signed integer, right? SLT, these two are signed integers. So you have to check, I think, B flag. And some, 0, a negative or 0 flag, right? Depending on the table on page number 36. This condition, okay, this one, right? Negative flag, V flag. These two are not equal, then condition is met, right? So simple instruction. Then the question is, when do you want to use SLT, Celestine instruction? According to RISC-V documentation, you can check. You can use SLT instruction to check overflow, underflow condition. Okay, overflow, underflow condition. So what does that mean? So a little confusing too, right? Let me explain other CPU, right? Other CPU like ARM, smartphone CPU. It has a general purpose register, and also ARM is providing special register called status register. So after doing some arithmetic operation, like addition operation, R1, ARM assembly code, R1, R2, R3. So you want to add these two and update. So in addition to generating, actual output, so this instruction is updating flags, NGCV. So those flags are updated based on addition output. And the thing is, this is a status register, so you can access status register to check those flags. You can, using software, you can read those flags to check if overflow or underflow happened during this, addition operation. And the same thing goes to x86. Intel is providing also, Intel x86 is providing E flag register, E flags or R flag register. Anyway, flag register is providing same information, NGCB. So it is software can access those flags. But in RISC-V, RISC-V does not provide, flag registers. Okay. Again, RISC-V does not provide RB. It is providing register file and ALU, but also, status register is provided. But inside the status register, you don't have, this flag information. But sometimes you want to check. You want to check if the overflow or underflow happened in computer. Okay, hold on. Okay, so you can use SLT. So SLT instructions to check overflow or underflow. Right? So this one is an example. Right? This one is an example for signed addition. Signed addition, right? Signed addition. I think these two. You want to add these two, T0 and T1. And you consider T1, T2 as a signed integer. And you want to check if overflow happened, right? Then you can use SLT, these instructions, right? Okay. So there is one, one usage case. And second usage case is this. Check out this, so data type. So test 1, test 2, test 3, Boolean data type, right? So if you write this code, you check, so A and B, right? A and B, integer, right? Signed integer. C and D, unsigned integer. And this one you are comparing what? Constant against C. So data type, test 1, 2, 3, Boolean data type. You can represent only 0 or 1. Then if you compile this code, then compiler will give you set less than. In this case, unsigned number comparison, right? C and D. So SLT U. And then second operand is constant, right? So using this instruction, IU, right? C, unsigned number and unsigned number, and I means immediate, right? So using this instruction, this code, this statement got implemented. Right? Okay, that is about for today. And on Wednesday, we will be talking about jump instructions. Right? RISC-V is providing only two, jump instructions. So it is very, simple. It will be simple discussion. Okay, that's it for today. I'll see you on Wednesday. Okay, bye.